I will watch those.
Okay.
Luckily, all my classes are being recorded.
Okay, cool. Thank you.
If there was a homework due that week or something, could I just turn it in early? Or?
Let me see. There could be, if that happens, you can either turn it in the week before, or if you have a strong reason, like tell me why you're around in a week, and then consider an extended week.
It's normal to present to
Are you able to travel?
No, I can't. But I won't be in school in the week.
Yeah.
We have to travel maybe like I cannot tell right
Yeah.
Like, how do you
I cannot guarantee even. Like I said, you can always make plans. You go on, any questions.
cite somewhere? Or is it figured out.
Because I'm really busy this semester.
No, you're good. I don't care.
So I cannot guarantee that so you can ask me.
Hello.
Hi.
Yeah. Yes.
With this course, what do you want to know about? Do you want to study, go through all this?
All right, let's get started.
Yes. I think we can follow this.
So last lecture we talked about the insertion in B+3, and today we're gonna do a quick review of that, then move on to the deletion that we'll spend 5 minutes on your lab 2, because we're ready to do your lab 2, okay? And then I will move on to external sorting. So to do an insertion operation in B+3, what you do is you do a search first. For example, in this case, when you try to insert this data tray with search key value equals to 8, you do a search, you identify this is the deep node that it should goes into, and then you do a split. And in this case, assuming we do a 2-3 split, we end up with 2 and 3 and 5 and 7 and 8 on the new leaf page. And then we copy the key up. Remember, in the leaf level, we copy the key rather than push the key. So we end up with okay, so that's what we end up with after the split. Then you take this key, this index entry, now you try to insert into this node, which is and 30, right? So you take that, try to insert into this. If I may duplicate this here. So it looks like this. Right? But now you have this 5 right here, and you try to insert that into this index node. And what you do is you split up one more time. So you end up splitting this node. What you end up with right? When you end up with is 5, this one will go here. Because that's the smallest search key value on this node. Then you have 13. Suppose we always do a 2-3 split, we end up with 17, 24, and 30. You follow me? Yes? And that 17, if you look at that entry has a pointer to this page right now. And 24 is whatever it is still pointing to. So there are 2 more pages here. I'm going to ignore them, right? Because there's no change to them. So 5, if you think about it, this after split, you have 5. Actually, sorry. So this pointer should be part of the 13. Right? It should be 13, and 17 actually point to. 17 actually point to this 19, 20, and 22. Right? That's the page indexed by the entry of 17. You follow me? And this is the page, this is the entry of 13, this is 5, and that leftmost pointer state, right? So this one stay right here. Okay? Now, after an index split, what do? You need to make a. But remember, in the index level, we do. So we push out this key, and we leave the pointer of that entry behind, and which becomes the leftmost pointer of that page. So you can narrow this a little bit. So this pointer actually comes from the index entry with 17. Then you make a new node for the root node. So that's what you end up with. Okay, that's what you end up with. So that's insertion. Now next, let's talk about deletion. So deletion is pretty much the reverse of the insertion procedure. So in insertion, when you do split. In deletion, you will do, obviously, you merge. You do merge, okay? So the idea is as follows. First of all, you do a search, you identify the leaf node containing the key you try to delete. Again, the setup is you try to delete a data entry. I assume that the record has been taken care of. So you're trying to delete the data entry from your index. What you do is you do a search first. You identify the leaf nodes that contains the search key value you try to delete. If it's found there, you delete it from the leaf node. The only trouble is that we need to maintain this environment, which is the number of entries in any page in a B cluster must be in this particular range. Right? That's the environment we must hold, except for the root page. Is that right? So, but when you do a deletion, it's possible that this value X becomes less than B. In particular, the only possible case is X become D minus 1, right? X become D minus 1. The first time it becomes, this is what we call underutilized. This page is not underutilized. What do? You first try to do redistribution, and if that fails, you try to do the merge operation. By redistribution, what I mean is, remember, towards the end of last lecture, I introduced the concept of sibling, right? Sibling refers to those pages that are on the same level with you to the immediate left or right of the current node and share the same parent. So for example, the sibling of this node is this one and this one. The sibling of this page, however, is only this page, but not the one to the right, because they do not share the same parent node. So you try to do redistribution first before you do the expensive merge operation. I'll give you an example. If I try to delete 19, that's easy, I just remove it. The page is not underutilized because in this case, it is not underutilized yet. But if I delete 20 from this page afterwards, so I delete 19, that's okay. But once I delete 20, this obviously becomes underutilized, right? Because you're using less than half of the capacity. What you do is you do redistribution. Who is your sibling node in this case? This is a sibling node. And what you do is you move 24 from that page to the current page. So it ends up with 22 and 24. However, when you move keys or data entries actually from one page to another, you need to update the corresponding index entry in the level above. So this is no longer 24, it should be updated to 27, the new smallest search key value of that page. In other words, you can think about this operation as you're doing redistribution of data entries through that intermediate index entry. So the path is like, come down. So you push this entry up, then pull it back down.
So we delete 19 and then delete 20 and 24 moves over. And then if we wanted to delete one more from there, would we redistribute from 2 siblings over and kind of make a chain, or do you just redo the whole tree?
No, when you delete, that's the next thing I'm going to talk about, right? If you now delete 27 or 24, actually, no, if you delete 27, you still can do redistribution from this node.
Yes.
But if you delete 22 or 24 at this moment, you can only redistribute from your immediate sibling node, not from, not go beyond that. Okay. So if you delete 22 or 24 at this moment, you cannot do redistribution anymore. You have to do merge. Merge is exactly the reverse operation of split. You know, if you think about it, it's actually fairly straightforward. So let me see. If let's say I delete 24, what I will do is I merge this page with this page. So I end up with a single page of 22, 27, and 29. And then I delete this page, deallocate this page altogether. Okay? When I merge these 2 pages, one thing that you need to do is to delete the index entry from the level above that indexes pages. Which means I will have to delete this index entry 27. Okay? Show this process. So right? Sorry. So when I merge them, I get rid of this page. 24 is gone, I got 27, 29. Of course, the corresponding RIDs are moved over as well. And the third is still index whatever that page is. Whatever that is. Okay? Now, this index entry is no longer useful because you deallocate the page, right? So you have to delete this index entry. Once you delete this index entry, the problem is this page becomes underutilized. This index page becomes underutilized. So you have to merge that with this page. You follow me? So you merge when you do the merge, what happens now? This is the interesting part, right? When you do this merge, remember, this entry right here, this 17, in the level above this current index page index level you're trying to do the merge operation. This was pushed up from that split operation, from the earlier split operation, right? Since merge is exact the reverse of the split operation. So when you do the merge, what you have to do? You have to pull it back down. You have to pull it back down. So what you do is, when you do the merge operation actually involves all three of them. So they will become the reason for that is imagine how you end up here in the first place is because you have a 17 here, you push up. Then you have to pull it back down. Right? Right, that's why it's exactly the reverse of the split operation. You follow me? So after that merge, what happened is you can imagine you get rid of this, that 17 comes back down. This leftmost pointer actually stays. You end up with a structure like this. Okay? Any question for this? Note that the leftmost pointer on this page, after you pull 17 down, become part of the index entry with search key value 17. Which is not surprising because this pointer was part of the index entry when you push 17, this value up. And it was left in this page as a leftmost pointer. Now you just merge them back to form that index entry. Okay? So that's essentially the deletion operation. Now I give you another example of non-leaf level redistribution because we have seen from this example how we do leaf level redistribution in a deletion operation, but we haven't seen an example where we do redistribution of keys in a non-leaf level. Here is my example. So suppose, imagine I have a tree like this. I will delete 24. So in this case, after I delete 24, I redistribute this key, I delete a key from here, right? I have merged those two nodes. The leaf level stay the same as in the previous example, so I do the merge, and I delete the index entry from here. As a result of the deletion, this becomes underutilized. In the previous example, I will simply merge them because I don't have enough keys here. Do not have enough search entries here. But in this example, I can do redistribution. I can do redistribution instead of doing the merge at that index level. However, what you have to pay attention to is redistribution at an index level is slightly different from redistribution at leaf level. The reason is when you do redistribution at non-leaf level, you have to involve this entry above, this entry from level above. Why? It goes back to how this entry was formed in the first place. This entry, 22, was part of this level to begin with. It was pushed up as a result of split. So when you do redistribution, you cannot simply involve these two nodes and do redistribution. Rather, you really have to do redistribution through something like this, involving this entry in the level above. In other words, in this case, if you do redistribution, what it ends up with is, if suppose you push two entries to the right, is you pull 22 back down to this page, and you push 22 up, then push it down again, and you push 17 up. So you end up like this structure. Okay? The reason for that, again, is because that split operation is done. Okay, with that being said, I think there is some examples. I will leave this for you to study yourself. Okay, we're almost done with B+3 discussion. So the only thing left is to review bar loading, right? So bar loading, yes.
I just have a simple question. So when we are merging, if the next leaf node is left page is full, we cannot merge it, right? So here the order is 2. So suppose for the last leaf.
Okay.
So if
in that case, you do redistribution in the first place. You don't do merge, right? If the next page is full, obviously that indicates you can do redistribution.
But I have to redistribute from this side to this side, and not just inside the page.
If you do redistribution in the index level, you have to redistribute through the entry in the level above. Involving that entry in the leaf level, you know, you just redistribute among these two nodes, but you have to remember to update the search key value of that index entry, right? So for example here, when you do redistribution, you have to update this value from 24 to 27 to reflect the new smallest search key value of the second page. Okay? One more thing I want to say about bar loading is, remember the bar loading procedure, right? What we do is go all the way back to the beginning of the discussion, which is this process, right? In this process, what I said earlier is you basically sort all these data entries, and then you pack them into leaf level pages by grouping B prime number of them together, where this is equal to B page size over your data entry size. So, for this. However, in practice, you don't have to use the full capacity of a page. The reason for that is if you do use the full capacity of a page, you end up with a tree who is 100% utilized. Any future insertion will lead to expensive split operation. So typically what you do is you use something, you use a value that's less than B prime, and we define this as what we call the utilization ratio of your tree, utilization ratio of your tree. A typical value for this is 2/3. You may wonder why 2/3? Why not 3/4? Why not half? And so on and so forth. The reason is there is a study, and they prove that given a B+3, any B+3, initial state of a B+3, right? And if you do random insertion deletion for arbitrary distribution of keys, if you do this long enough, this utilization ratio converts to when sequence size goes to infinity, where S is a sequence of with arbitrary distributions. Okay, so there's a result that shows this. Okay, that's why people typically just use 2/3 as the utilization ratio for the tree. Okay, so that's the only thing I want to talk about for bar loading. And bar loading, the other benefit of bar loading is if you already have a set of records, right, and you know which is the search key to build index over. Bar loading is much more efficient in terms of building a B+3 out of your data set versus inserting record one by one. Clearly, number of I/O wise. You can actually prove this. Okay? So that's another reason why people do bar loading. And I think that's it. Okay, that's the discussion on B+3. So now I'm going to show you lab 2. So here is your lab 2. You can get it again from the homepage. There's the link. Today is October 6th, so I give you about 2 weeks time, a little bit more than 2 weeks to work on it. So lab 2 is about B+3 and buffer. So remember from your lab 1, you actually interact with buffer a little bit, right? But what you didn't implement in lab 1 is a replacement policy for your buffer. So in lab 2, you will implement that. We give you the freedom to choose whatever replacement policy you want to use. You can use RRU, MRU, LFU, whatever, as long as you document that clearly in your record. Okay? And so that's essentially the first exercise, which is to implement that buffer replacement policy for the buffer. Now once that's done, then you will implement search in B+3. And in this particular test case, we use a fairly small size buffer. We give you 16 pages of your buffer. So if you do enough search and insert and deletion, you will run out of space of your buffer, so we will observe some replacement activity. We should be able to observe that if you have implemented your exercise 1 properly. Okay? Then you do your search. Search is fairly straightforward, right? You can implement this in a recursion fashion, right? Just going down the tree, right? And then you do insertion. Then you do deletion. And after you've done all of this, you're done. That's your lab 2. Okay? I think this lab is not that hard. The only tricky part is that most of you, if not all of you, are used to write code in the RAND model. Right? So basically, you allocate some objects, you modify the object directly, then you operate in that space. Right? However, in our case, you can no longer do that because every node, like you see from here, is a page. This page. So whatever you do, whatever change you try to make to that page, you have to go through buffer. You have to pin the page first. By pin the page, it brings the page to the buffer. You make changes, and after that, you need to remember to mark the page as dirty, so that buffer will later on, whenever buffer tries to replace a dirty page, it will write it back to disk first, so that your change is permanently reflected in your database. If you don't do that, if you still try to write code in this RAND model, your code will not work, obviously. Does that make sense? So that's the tricky part you want to pay attention to. Other than that, the insertion deletion algorithm is fairly straightforward, in my opinion. I mean, I would recommend, you don't have to, but I will highly recommend you use a recursion approach to do insertion and deletion. I'll give you a simple example for insertion. You find the root node, you do insertion. And you find which subtree you try to insert this entry to. Then you call this subtree, you view that as a B+3. Recursively, you call the insert method itself again. Now this subtree, so this is the root node, right? Suppose you find this is where you want to follow. You view this as another tree. That's the picture. So you call your insert, where initially insert is called on this tree with this entry, whatever. And then when you do in this code, you identify, okay, this is the part this entry should go to. Here you call insert with the same entry, but now with this tree T prime. And this method should return either null value or success, a flag. Either return that or return you an entry. Why? If it's inserted successfully into the subtree, maybe the subtree has gone through some expensive reorganization, but the split doesn't propagate all the way back to the root of the subtree. So from this point of view, you don't see what's going on under the subtree, so you don't worry about it. But if this is a super expensive split operation that goes all the way back here, resulting that this is splitted, and there's the entry, as a result, there's the entry being pushed up, then by calling this method on this tree, you wait until it returns. If it returns, entry means that, oh, it's split, go all the way up here. Then I need to split that block. You don't have to split. I need to insert this entry, and maybe I need to split that block. So that's the basic idea of insertion. You do this using a recursion approach. You follow me? And deletion is something somewhat similar to this. Okay? So I do encourage you to start early. Lab 1 will give you sufficient amount of time because it's the first time you work on simple DB, so it will give you sufficient amount of time. And Lab 1, in my opinion, is fairly straightforward. But Lab 2, it becomes a little bit more challenging than Lab 1. I give you 2.5 weeks. And when Lab 2 is due, we will immediately release Lab 3. And Lab 3, I will give you another about 2 weeks. I'm thinking about doing 5 labs in total. So after Lab 3, we still have 2 more, at least 2 more labs coming up. Okay. So the good news is after you're done Lab 2, and when you're done with Lab 3, you will be able to type SQL and execute against your code. And then you will feel that excitement, or fulfillment at least, of that you build something that's useful. Okay. So I think by Lab 3 you will feel the reward at least. Okay. And the other comment I want to make is the way we distribute the lab out is I'm not going to give you a solution to previous lab. That being said, when I design Lab 2, we spend extra effort to make sure we only give you the code you need to implement for your Lab 2. Of course, each lab, subsequent lab, builds on the preceding lab, which means Lab 2 does depend on your Lab 1 code. Okay, Lab 2 does depend on your Lab 1 code. Instead of giving you a solution for Lab 1 code, I will ask you to use your own Lab 1 implementation. If you have passed all the test cases, there's a fairly good chance that your code should work just fine. Of course, there's a slight chance that your code might not work because there are bugs that's not captured by our test cases. And this actually also gives you incentive to make sure you properly implement everything, because if you don't, it's a cascading disaster, right? It affects you Lab 2, Lab 3, and Lab 4, so on and so forth. So that's why I don't call this as Lab 2, I call this Lab 2 supplement. So it's a supplement set of code to whatever code you already have from Lab 1. What you do is you unzip this and copy this into your Lab 1 folder. It will not overwrite anything, so don't be worrying about that, because everything will give you a new source code. You copy them and they observe the same structure, folder structure. So you simply copy over, and that together with your Lab 1 code will become your code base for your Lab 2. Does that make sense? By the time you do submission though, I do want you to rename your folder to from Lab 1 to Lab 2. Does that make sense? Whatever product, if you're doing this in Eclipse, you want to rename your product from CS6530 Lab 1 to CS6530 Lab 2. You have to make that simple change. Okay? Other than that, I think that's all I want to say about Lab 2. Any questions so far? Okay. You should start early, right? Together with the other reason I give you 2.5 weeks is I'm aware that you're also working on your homework too, which is due 1 week before this. I give you a week in between. But I have assigned released homework to last week, and you should be working on that for a week by now. If you haven't worked on it, that's your fault, not my fault, right? So you are given sufficient amount of time, in my opinion. Okay. All right. So that being said, let's move on to the next lecture. Oh, by the way, I want to spend a few minutes on revisiting this table here that we done a long time ago. Oh no, this one, access method. So going back 5 or 6 lecture time, and at the point we talk about access method, I skipped this part. I said there is a discussion on index, and I will come back and revisit this when we are done with the discussion on hash and the tree-based indexing structures. We're finally done with all this, so I think I can skip all of this, like classification, what's a cluster index, what's an unclustered index, and what is a cluster file, and we are all clear about this, right? In particular, cluster file is a special cluster index where you essentially do not have these levels. You do not have the leaf level at all. Imagine you get rid of this level and it index directly to the records. That becomes a cluster file. And of course, the records are sorted according to search key values. Okay? So there is also some discussion on composite search key. This one is fairly straightforward. I ask you to read it yourself. I'm going to skip this from my lecture. Right? Now I'm going to try to fill out this table. Remember, we've done this table before. Right? What's the insertion, deletion, and operation cost for each different structure, different access method. So we're going to try to fill out this table now. In order to fill out this table, we have to be clear about the assumption we made. For example, what's the utilization ratio of your tree, and so on and so forth. Right? So here are some basic assumptions in the analysis thereafter. Okay. So for indexes, whether it's hash or tree-based index structures, we assume that data entry size is 10% of the size of the record. This is not always true, but we just make this assumption here. Okay. So that means that keep in mind when you are working on your homework or when you later on work on your exam problems, don't copy the formula here because the condition might be different. Don't simply copy the formula, right? You have to understand this analysis and apply to the particular setup you are given. So in this case, we are assuming that data entry size is 10% of record size. What that means is, what that essentially means is this B prime is 10 times of B, essentially. What that essentially means is B prime is 10 times of B. And for hash indexing structure, we will assume that there are no overflow buckets. And we'll assume the page utilization ratio is 80%. What that tells you is, if I have n records, each page can hold B records. That's assuming 100% utilization ratio. Now with 80% utilization ratio, this translates to what? This many pages in total. Okay? And because you have this many pages in your file, and given this operation, this also translates to I have how many pages in the leaf level. In the leaf level, I will simply have this many pages in the leaf level. Because in my leaf level, my page capacity is 10 times of my page capacity in the file. So given the same number of entries, so you have this many records means you have this many. In other words, this basically is n divided by B prime. That's how this calculation comes from. That gives you essentially. Given this, and I simply do that. You follow me? Okay. Now this is for hash. For tree-based indexing structure, again, for 100% utilization, you get this. This many pages. And I already explained to you for B plus tree, we have this 2/3 results, right? So we'll assume 67% utilization. This roughly translates to 1.5 over B leaf level pages when you do 67% utilization in the leaf level. Sorry, no, not in the leaf level, in the data file. How many data file pages you're going to have when you use 67% utilization ratio. And for the same argument, this translates to leaf level pages. You follow me? We use n prime to denote the leaf level pages, right? So, any questions so far? That's the assumption we have, okay? Now, that being said, and also now let's try to fill this table, right? We have done this entry before for heap file and sort file, right? Let's look at cluster file. What's the cost of doing scanning all records? Well, that's simple. You simply scan all these pages. What's the cost of doing equality search? Well, for cluster file, if you think about it, as I said, a cluster file is nothing else but ignoring this level, right? Essentially, your data file becomes your leaf level pages. And what's the height of bpath tree? For a leaf level with n prime pages, what's the height of your bpath tree is? We did the analysis last time, right? Which is this. Follow me? And your n prime for a cluster file is what? It's this, not this, right? This, because you skip this level for a cluster file. So n prime in this case is simply this. That's why you got that cost over there in that table. You follow me? For equality search, it's simply the height of the tree. Assuming, again, there's another implicit assumption here is that there's only one matching record for equality search. Otherwise, you have to plus a number of matching pages, which is, suppose your query cost is T, you have to do T over B. There are T records you range, each page holds, you have to do T over B times 0.7, so 1.5 this. Because your page is 67% utilized. T over B assuming 100% utilization ratio, right? You follow me? Now for range search, what's the cost? Well, I think I need to fix this part. I forgot to add that 1.5. Okay? For the reason I have just explained, actually. Okay? Now for insertion, again, assuming we're not doing the expensive split operation. Assuming that's the case, what's the cost of insertion? Well, you do the search, and you update the page, and you mark it dirty, you write it back. And so you have to plus 1 to counter for that write operation. You do not plus 2. Why? Because the reading of that page is already accounted for in this height of the tree operation. Same goes for the deletion. In the worst case though, insertion and deletion, in the worst case, the cost is simply 2 times of this. Why? Because in the worst case, a split may propagate all the way up to the root of the tree. That affects about the height number of pages. And you have to count for the height of the tree number of pages for the search, height of the tree number of pages for the split operation, in the worst case. So it's just 2 times of this, in the worst case. Any question on this? Yes?
Is that a question on the homework? So when we're doing calculating IO costs, are we assuming no splits and
Oh, we assume this case. Unless otherwise specified, you assume this. And that's why the reason we assume this is because we assume the tree is 67% utilized, so most likely you will have space on any page. You try to insert it. Okay? So that's cluster file. Let's expand this to unclustered index and cluster index. So here, okay, I think it's better to update this table to make it clear. I don't know it's either how easy it is to update this table. This is to assume that we're using 67% utilization ratio for the data file as well. Otherwise, it's N over B if you assume 100% utilization ratio, right, for the data file. But let's be consistent. Let's assume we're using 67% not only for the pages in index, but we're also using the same utilization ratio for the data file. That's why that's the scan cost For ecology search, this is the cost for unclustered index. Why? Because your n prime in leaf level is this, as I just argued. So it's hydro tree plus 1. And once you understand that, the rest is fairly straightforward to understand. Here, y plus 2, why not plus 1? The reason is you need to update the data file. Hydro tree only give you to the leaf level, you need to go fetch that page in data file, then plus 1 for the write operation. But for cluster file, only plus 1 because by the time you're done with hydro tree number search, you are already in the data file because the leaf level essentially is the data file. That's the subtlety over here. Any question for this? I think I need to update this as well. Come on. How do I get back? Okay. For hash, no, this is what happens. The only thing is for range searching using a hash index, you basically have to do a linear scan. Of course, in practice, sometimes you can do better. If you do a range search of A to B in hash index, you can translate this to multiple ecology search queries. Until B, right? If it's a small range, maybe doing this is better than doing a linear scan to find all your records within the range. But typically, if this range is fairly large, doing this many ecology search probably is worse than just do a sequential linear scan. That make sense? Finally, one thing that's missing from this table is what happened to cluster tree index, but it is not a cluster file. Then in that case is similar to this unclustered index. The only difference is for range search, the cost is not number of matching records. Right? Because number of matching records, for unclustered tree index, you have to pay 1 IO for each matching record, right? For cluster index, it will be number of matching record, which is T essentially, over B. Because you can do a sequential scan. Of course, you have to cater for the utilization ratio of 67%. And the other thing that's missing from this analysis is not in the unclustered index case, not only you need to pay this many IOs, 1 for each record, you also need to do this. To cater for the fact that you need to fetch those leaf level pages containing the data entries in the range in order for you to do the matching. Maybe I should be explicit. I will update the slides later. Pause. Sorry, it's not T. Which is essentially a T. So I just. I think that will be clear. Okay? Any question on this? Is it right? Yes. Yes. Okay, I think that's all. Come back to axonal sorting. Now let's do axonal sorting. So for axonal sorting, I see some puzzle face, so maybe I should just write that equation out. Okay? Do you follow me? That's what it is. And of course, b prime equal to 10 over 10 times b. In this case, of course, the reason we have this is we assume that entry set is 10% of record size. That might not hold if I change my problem setup. Right? But and to be precise, the number of matching, in this case, number of pages with matching record, that's essentially T over B. Of course, if you assume 1.5, that's essentially what it is. Okay? In this case, if you assume 100% utilization ratio, this is essentially T over B. Okay? Any question on these formulas? Like I said, I emphasize one more time. Okay? Do not memorize formula. You have to understand how they are arrived, how they are derived. Okay? So let me update this in case I forgot. Okay. Let's come back to access method. External sort. This is a fascinating topic, right? So sorting, I don't have to argue for you. Sorting is important, right? Sorting is the foundation of one of the foundation for computer science, essentially. A lot of problems are related to sorting. People are fascinated about sorting, right? So they are actually sorting competition every year. Who can sort this data set in the shortest time. So you might wonder, okay, I know sorting. Why you are giving me a lecture on sorting? Quick sort, merge sort, bubbles, even as we mentioned as bubble sort, right? Check, swap, n squared operations. On quick sort and log in on expectation. Why we need to talk about sorting? The thing is, so far in the implementation of sorting, all the algorithms you guys know assume, again, random model, right? You assume random model, which is you assume that your data set D fits in your memory. In other words, N over B is less than M over B. Remember, M is your size of memory. In terms of how many objects you can hold, N is number of objects in your data. B is how many objects you can hold per page. So implicitly, all the sorting algorithms you have done so far have this assumption. When this is no longer the case, you can still use existing sorting algorithm to do it. Let me use bubble sort to illustrate, right? So what is bubble sort? Each of this is a single attribute. So what is bubble sort? Compare and swap if needed. That's space 1, space 2, space 3. In each phase, you do n operations. N minus 1, N minus 2. You only need to check against everyone coming behind you. You don't have to check against items before you, because after swap, they must be smaller than you. So in main memory, what's the cost of this? What's this value? Well, you can. And each is just n plus 1, and you have n such pairs, and we do it by half. You have n over 2 such pairs. Each pair, the sum is n over n plus 1, so it's just this. You follow my idea? So this is roughly order n squared. As bad as it is, it's n squared CPU operations. Suppose I consider compare and swap in one instruction, so it's just n squared instructions. Do you follow me? But if you assume, let's say in the worst case, I only have my memory m equal to 2. What happens? Anytime you can hold only 2 objects in the memory, right? What that means is you load these two, compare, you swap. Write it back to disk, the first one back to disk. Then you, so these two, do this, you do this. It's very simple to say the number of I/O operation is how many I/Os. You are essentially paying this many I/Os too. So when you do that, this no longer, if you think n squared is bad, if you do n squared I/O, this is nothing. N squared CPU instruction compared to n squared I/O is like nothing. So in other words, if n is, let's say you are trying to sort 1,000 items. Using this very naive algorithm, you end up with instructions, 1 million instructions, which is bad, but you can afford that, right? One instruction is about what? One CPU instruction is microsecond, right? Microsecond is about 10 to the power minus what? 10 to the power minus 6 in that level. So you can do this roughly in seconds. It's still audio seconds. You can do 1 million instruction in about seconds. Do you follow me? So you use bubble sort to sort 1,000 items. It's really bad, but you can finish this in about seconds. Now, if you talk about n squared I/Os, these are roughly, when you go from this level to this, these are random I/O too, because every time you load only 2 items, and you hold, and this rotates. By the time you read the next item, so it will become a random I/O. Each random I/O is in order of milliseconds, right? So 10. So suddenly, from roughly, assuming CPU instruction is microsecond, this translates to about 1 second. Now you're talking about 1,000 seconds. Do you follow me? Of course, you can argue, okay, let me use quicksort. But the fundamental constraint still applies, right? If you only can hold 2 items, what do? You hold the pivot. For quicksort, what do you do? You select a pivot, which is your pivot, right? Then everyone compare against this guy. Then they go to either left or right, depending on it's smaller or greater than the pivot. Then you recurse. Do the same thing here, do the same thing here. Each phase is obviously the n operations. How many levels you have to go down before they become 1? Suppose you choose a good pivot that always in the middle, you have log n levels. So it's n of. On expectation is a randomized algorithm, depending on if your pivot is really bad. For example, you happen to choose the smallest one, then everything goes here. There's nothing here. Then effectively you did nothing. Does that make sense? But you cannot be that unlucky, right? If you're that unlucky, you should go back elsewhere. drive to Wendover and buy something. I think you will win something. You know, but actually, I took back what I said. If you are that lucky, don't buy lottery because you cannot be that lucky twice in a row. Seriously. Does it make sense? So, okay, but in this case, it's n log n CPU operations. So n, if n equals to 1000, n log n is only what? Is this is roughly log n is suppose log n 2. This is 2. So this is roughly 10 to the power 4. If your CPU instruction is 1 microsecond, one instruction, this translates to about. So you can sort this 1000 item in only 0.01 second versus 1 second. Much better than bubble sort. 100 times faster than bubble sort. However, if I give you only 2 memories, what happens? Let's do the math, right? Let's do a rough estimation. Again, you load the pivot. You only have 2 memory space, right? So the pivot must go in, and you load each one of these in turn. Does that make sense? So each phase, that translates to n IOs. You still do log n phase, so total is n log n IOs. Do you follow me? And these are random IOs too. Even though you're reading item one by one, but by the time you read this and you do the comparison, you do all that, you coming back to the next one, it's already rotate over. Actually, it's 2 times of this because you have to read and you have to write it back to either here or here. So it's 2 times of this many IOs. You follow me? So let's do the math. So it's about 10 to the power 4. We do log 2. So this many IOs. Each suppose is 1 millisecond. Translate to about 20 seconds. You may argue, oh, this is way better than this, right? But do you notice that it's already worse than the naive bubble sort? When you do not have enough memory to hold all your items. Even though you're using quicksort, I'm using the naive bubble sort, but because I have enough memory space, you don't. I beat you by 20 times. Question is, can we do better? With only 2 or 3 memory space. In particular, an open question is, quote unquote open. This is not open to human being, open to this class. Right? If you think about human being as a whole. But imagine if something happened outside this classroom while this classroom is going, and we're the only one left, then this is open, right? It's open, right? So open problem is, can we do in other words, instead of doing this many IOs at item level, can we do this many IOs at page level? Make sense? So imagine, think about how you do search over. How do you do search over a sorted file? You call it search. What's the cost of this? It's log 2 of n more b, right? It is not log 2 of IOS, right? Does that make sense? Because you load a page, then you try to find whether the value is greater than smaller, then you load the next page from either left or right, the median page, right? But you do this at page level. You don't do this at you can of course do this at atom level, but that would be extremely stupid if you do that. You should do at the page level. And there's a huge difference between the two. Why? Typical value of B is 100. Let's just do some math, right? Let's say n equals 1,000. We just do, this is about 20 seconds, right? If we do this, suppose we can do this, what's the cost? Right? This is about 3 or 4, right? 3 something, so it's 30 what? IOs times milliseconds. That's roughly 0.03 seconds, which is close to what you get in room memory. Suppose you have enough memory to hold all 1,000 items, but I have only 2 memory space. You have sufficient memory space, but I'm getting close to your performance. Does that make sense? So make a huge difference, right? So the open problem, can we do this? That's what we're gonna do next, okay? That's what we're gonna do next. Furthermore, to challenge you furthermore, suppose we can do this, can we do this? This is log base 2, this is log base of your memory size. And there's a huge difference here, right? Because if you do that, this is a big log, right? Let's say log 10. And this, instead of 30, it becomes just 10. So this becomes, instead of this, become, it's almost as you have sufficient memory, even though, in fact, you don't. Do you follow my analysis so far? Okay, so the two big question is, this is Q1, this is Q2. Okay? So we're going to solve Q1 first, then we move on to solve Q2. So to solve Q1, to solve Q1, I give you a string setup. Suppose you have only 3 memory space. So M equals M over B. Okay. You have 3 pages. You have 3 pages. Okay? 3 pages. 3 pages. You have only 3 pages. That's fairly small, right? So each page, let's say each page is what? Each page is 4 kilobytes. This is what? This translates to a memory size of only 12 kilobytes. But when I was a little kid, when I was in high school, that's the computer we had. No, it's megabytes. Sorry, I took back what I said. It's megabytes, it's not kilobytes. So I never used computer with kilobytes. Sorry, I did use computer with only 16 megabytes of RAM. So 12 kilobytes, and I want to sort, let's say, give you a string, I want to sort 1 terabyte a day. You say, how can that be possible? That's impossible. You only have 12 kilobytes, how can you ask me to sort 1 terabyte? The answer, of course, is yes, you can do the things we argued just now. You can use quicksort or bubble sort, and just implement the way it is, but it will be extremely inefficient, I'll argue for you, right? Extremely inefficient. Can we do it efficiently, the question, right? The answer is yes. Here is how you do it. So I'm gonna do this setup like this. Remember, I have 3 pages in the main memory, right? So what I do is I organize them like this. So in the first round, I simply organize them like that. 1, 2, 3, page 1. Okay? And suppose that's my disk. And these are my heap file, right? That's my heap file. My heap file. And conceptually, I view them as altogether I have N or V pages, right? Conceptually, that's the view. In phase 0 or path 0, what I do? I do it very simply. I load 3 of them into the buffer, sort. Here I use the in-memory sorting algorithm. Whatever you want to use. You can use bubble sort, but highly recommend not to use bubble sort. You use quick sort. Use something that's efficient. In-memory sorting. That's okay because this involves no I/O. Everything is in-memory. Then you write the output to disk. Now, what's special about these 3 pages are these are now sorted. Within themselves, they are sorted. Does that make sense? And then what I do, I load the next 3. Then I get another something like this. I continue to do this until I end up with the last 3 pages. You may argue, wait a minute, N over V mod 3 might not equal to 0, right? But that's fine. If that's not equal to 0, this can only be 0, 1, or 2. 3 cases. I'm showing you equal to 0 case. If it's 1, then the last one looks like this. If it's 2, the last one looks like something like that. Does that make sense? Let's consider the general case where, without loss of generality, I will consider it's just equal to 0. Now, conceptually, I call this as a round. And this is in our case, it's N over 3 round because N over V divided by 3. Okay? Is that okay? Now, what I do is, imagine I now copy my memory over. So that's my memory. So now I'm going to do pass. By the way, these are written back to disk. Because you cannot hold this in memory, you don't have space. You read them back to disk. So this is only disk. These guys are on disk. Now on my pass 1, what I do? I'm gonna organize my 3 pages like this now, instead of like that. Here is the trick. Okay, here is the trick. What I'm gonna do is, I'm gonna look at the first 2 rounds. I load the first page of the first one into here. And load the first page of the second round here. Is that okay? So now they are filled with data. This is empty. How many data I have? B on each page. Must be, because that's the size of my page. I maintain a cursor that starts moving these cursors in order, of course. The smaller value is pushed here, so I move the cursor. If now this is still smaller, I push it in. At some point, I may reach a configuration like that. And this is filled up with B items. what do? I write into disk, and now this is empty again. Does that make sense? Now I continue. At some point, I may reach a configuration that everything here is checked. But this is somewhere still here, right? What do I do? Can I keep pushing this? No. What you do is load the next page of the same ROM. Then you continue. Because within each ROM, they are sorted. At the end of the day, what do you get? When you finish everything, what must have occurred? You have six pages that's sorted. That's your first one. And then what do? You move on to the next two rounds. You do the exact same operation. Move on to the next two rounds, so on and so forth. At the end of the day, what do you get? Of course, I cannot, I cannot assume that this may no longer equal to 0. Even if I assume 3 equals 0, this may not be the case. But doesn't matter. The last one is always a special case. It has anywhere from 1 to 6 pages. 1 to 6 pages. That make sense? Depending on what's the size of the last two rounds you try to merge. Or you may not even have two rounds to merge, because in the previous round, it's not an even number of rounds. So you have one round just by itself, then you don't have to do this merge operation. You simply copy over. So the size is anywhere from the size of the last one is anywhere from 1 to 6. How many rounds in total you have, by the way? Here, how many rounds you have? You have n over b divided by 3 number of rounds, right? How many rounds do you have now? How many rounds do you have? You are merging every 2 rounds into a round. So you reduce the number of rounds by half. So roughly you have, of course, take the floor of this. Sitting on this. Should be sitting on this right here, because it might not be a modular of 3. So it should be sitting on this. So roughly like that. Then what do you do next? I don't have to show you anymore, right? You do the same thing. But now you're merging rounds of 6 pages into a round of 12 pages. But at the end of the day, you reduce the number of rounds by half. How many disk space you have to do in order to reduce to a single round of all sorted? Well, the number of passes you have to do is essentially log 2 of this is the number of rounds after pass 0. Every time you reduce by half, you need this many passes to reduce to a single round. Right? You divide this number by 2 every time until it becomes less than 1. That's it. Of course, you have to cater for the first pass. That's the total number of passes you have done, right? But what's the I/O? What's the total number of I/Os? In each pass, whether it's this pass or this merging pass, how many I/Os you are doing? You are loading all the pages once, you read them once. At the end of the day, how many pages you write? You basically read this many pages. And at the end of the day, I don't care what's the order you write them back. At the end of the day, you write these many pages. So in each pass, you are doing simply these many arrows. And this is constant, right? This is just so Q1 solved. Q1 solved. Question 1 is solved. Okay? No longer open problem. No longer open problem. So here is example. And look at this example yourself. But essentially, it's exactly what we're doing, right? In this case, it's very conservative. In the pass 0, I load only a single page and sort them. I basically sort each page. I don't even do this. I simply load a single page. So you pass 0, you don't have divided by 3 factor. You just have this many pages. You load one page, sort them. But you can actually do better than that. Then you start merging them and so on and so forth. Right? So that's the output. And that's how you get this analysis here. Okay? I think I'm going to stop here, but I will let you go into your break with the challenge of Q2. Right? How do you? What if so far what we said is we have 3 pages, right? But what if your buffer has same thing here? You may have many more pages. Of course, you can argue I only use the first 3 pages. The rest I ignore. I don't use them. Thank you for your offer. Not going to take it. But obviously, intuitively, you should be able to do better, right? I give you $3, you can do this. If I give you $300, don't tell me you only buy the same set of candy, right? Come on, you must be able to do something better than that. I mean, if you give to a person, right? If you give to the government $3, 300, probably only make a difference if you give them 3 million versus 300, right? 300, 3,000, same effect. So the question is, can you do better with bigger than 3? Okay, that's the question number 2. We will do that after the break, and enjoy the break, but at the same time work on your lab 2 and your homework 2.